This is me, and Gábor Rácz is the student who's working on this project, which is a new kind of simulation of the infinite universe. And these are Gábor's slides, so excuse me if I talk about an entirely different thing which is in the slides. I will try to follow the slides, but also my own logic of explaining this problem we are trying to solve here. So what we are interested in is the large-scale structure of the universe. We know from the observations of the very early universe, so the cosmic microwave background radiation, that density fluctuations are very tiny in the early universe, only 10 to the minus 5. And if we look around with an optical telescope and look at the nearby universe, which is the universe almost 14 billion years later, we see a very high density contrast. A galaxy is a density contrast of 10 to the 6. And we also observe some clustering of these galaxies, which we call the large-scale structure. So galaxies like to be in galaxy clusters, and then we see even bigger structures. Superclusters, filaments, huge voids where there are no galaxies at all. And the only way to somehow investigate this structural formation problem is to run computer simulations. And this is because the whole problem is nonlinear. So when we have gravity acting, it will pull the matter together. That will increase the density contrast, which will increase the gravitational force, and the whole thing becomes nonlinear, and we cannot follow this in theory. There's no way to describe this analytically. So from the early 80s, people have been running cosmological simulations, and these are dark matter simulations. Most of the time, there's no hydrodynamics involved. It's just particles and gravity. And I'd like to talk a little bit about the current state of the art. So we use the standard cosmological model here. We built this model into the simulations. So all the assumptions of this model are built into the simulations. We don't try to actually figure out how this model actually works from these simulations. We just want to match the end result to what we see around us. So there's all kinds of constituents of these models, like dark energy and cold dark matter. This doesn't really matter here. I will point out where the actual cosmological model matters in these simulations. Okay, so this is what we see around us. Here you can clearly see that galaxies tend to be on these extremely large structures. Some of these could be explained by the result of gravitational forces acting throughout the age of the universe, so these almost 14 billion years. But some of these structures can only come from the initial conditions. Okay, so how these cosmological simulations are done? So the first thing is that the universe is infinite. So we have to build this somehow into the simulations. The other thing is that space expands, whatever that means. We call this the Hubble expansion. So if I pick two galaxies randomly, they will just fly away from each other because of this global or cosmic expansion of the space. And we have to build this into the simulation also. Of course, it's tricky because on small scales, there's no such expansion. So if I look at the galaxy cluster, for example, we call that a gravitationally bound system. So that doesn't expand. And you will see that it's impossible to simulate this right now. So we always assume this Hubble expansion on all scales, so we cannot distinguish in these simulations the gravitationally bound systems and the expanding systems. So what can we do when we have an infinite universe? We use periodic boundary conditions. So the simulations will be done in a cube, and the expansion will be put in by rescaling the coordinates and the velocities according to some equations that we can calculate from Einstein's field equations. And what we try to change here is this periodic boundary condition problem, because that introduces a lot of weird things. For example, I have to go a little bit further with these slides. So, of course, periodic boundary conditions means that what goes out here comes in here, right? So it's a periodic cat. And this introduces a lot of problems. For example, if we look at the gravitational force on some particle, which is located here, because we have to take into account more than just one image of this periodic box when we calculate the force. The gravitational force is not shielded. It's not like the electromagnetic force, which is practically not infinite, because you have always some kind of shielding effect that doesn't act in case of gravity. So you feel gravity from cosmic distances. So if you have a simulation box of certain size, let's say 5 times the scale of superclusters, then you have to take multiple images into account when you calculate the force on a given particle. Force is just the gravitational force summed over all the other particles. But if it's done in a periodic box, you get weird force fields like this. And so the gravitational force isn't isotropic anymore. And this is a well-known problem, yet no one tried to solve this. So what we attempted to do, let's take a look at how these simulations are done. So one of the most well-known simulations is the Millennium simulation, which is almost 10 years old now. And this is the end result. So this is just dark matter density that you can see here. The brighter parts are the galaxy clusters, superclusters, and these thin structures are called the filaments, and these big black and blue voids are the voids, so the empty areas. Of course, there's some dark matter there, but there are no galaxies. So when we observe with the telescope, we don't see anything there. And to run these simulations, you need to be tricky. Especially 10 years ago, people need to be tricky. There were no GPUs, so everything had to run on a grid. And of course, the number of particles is in this range today. But for this Millennium simulation, it was 10 to the 10, so 10 billion particles. And if you don't have a shared memory system with big enough CPUs, you use a grid, then you have to communicate a lot of information over the network. So what these people come up with is that they distributed these particles across the nodes such a way that the communication can be minimized. So how can you do that? You somehow split up the entire space. So you use some kind of space filling curve and try to put the same number of particles on each compute node, which isn't that trivial, because if you look at this figure, the point masses are highly clustered. So they are not evenly distributed across space. So when you want to distribute these particles over a lot of computers, you have to be tricky to put the same load on each of the machines in terms of memory and in terms of computational needs. And so within a machine, it's quite easy to calculate the forces. It's an n-square problem. But of course, if you wanted to do a direct n-body code and use multiple machines, then you would need to copy all the particle positions in each time step to all the other machines, which was prohibitive. So they come up with a simplification, which is basically organizing this whole simulation in a tree-like structure, that every compute node is in the leaf of this tree, and they do direct n-body only on the particles that are on the particular node, and then calculate some average over the forces that act on faraway particles in some kind of expansion, like spherical harmonics expansion, and then you only have to ship across the network these harmonic coefficients and not the particle positions themselves. Okay, so far so good, but we wanted to change this also because we wanted to use GPUs. And it turns out that it's quite easy to do n-squared brute force calculation on the GPU, but everything else is more difficult. So we didn't want to do a tree code on the GPU, and we didn't want to do a periodic simulation. So if a simulation is not periodic, the universe is not periodic. As we observe the universe, it's more like a spherical structure. Of course, we are in the middle. We don't have any special position in the real universe, but we are in a special way that we look the universe from the Earth. And what we see is that as we go out and out to higher redshift, we see older and older stages of the universe. And somehow, the resolution also decreases as we observe further and further galaxies. Actually, we see less and less galaxies as we move out, because we only see the brightest, the most massive galaxies, and we see everything with high detail in the middle. So what we figured out is that we can use some kind of stereographic mapping of space onto the surface of the sphere and compactify space somehow. And this way we can end up with a simulation where we have very high resolution near to the center, and then the particle masses will just grow as we move out and out. The space resolution will decrease as we move out and out, further away. And of course we will have an infinitely large particle at the very end, which we will take as a boundary condition. So this is the setup that we wanted to solve, and we wanted to solve it on the GPU. Of course, everything changes a little bit because space expansion has to be taken into account a different way, but that's just math. Now let's get to the programming part. These are minor details. This is how you calculate the force. You can use all kinds of theorems here to simplify the force calculation. And then the force is not the traditional Newtonian gravitational force, of course, but you have to take into account these so the space expansion factors here, but otherwise it's just a Newtonian. These are just Newtonian two-body interactions. Okay, so what we do is, because we discretized space, it's enough to have much less particles to simulate a big chunk of the universe as compared to periodic simulations. So the main point here is that we only simulate the very center with high resolution, and everything that's further away is lower resolution. If you do it in a periodic box and you have equal particle masses, then you have lots of particles. And one interesting quantity in these simulations is the correlation function. And if you have lots of particles, then for the short scale correlations, you get the correlation function with extremely high signal to noise ratio, whereas if you go to higher distances, then the correlation function will be extremely noisy. And these types of simulations where you have a varying density resolution, you can balance the noise of the short scale correlations and the long scale correlations very well. And this fits much better to the observations, because observational data is exactly like that. So what can we do here? Because we have much less particles than in typical simulations. We can put everything on the GPU. But the hard part is the force calculation. We use a direct n-body code here. But because we have much less particles, we can always shift the particle positions between GPUs, and as I will show, between compute nodes. Okay, so what Gabor did, he basically went through all the stages of the simulation parallelization, because he started out with a single-threaded code. And he learned how to do OpenMP, or how to use OpenMP to parallelize the code over CPU cores. And when that wasn't enough, then he figured out how to use multiple GPUs. Of course, copy the particle positions between the GPUs in every time step. But then when that wasn't enough, he figured out how to use MPI to do this across multiple servers with multiple GPUs. So we have this fine hierarchy of parallelization. And the only thing we parallelize is the force computation, the n-squared problem. So everything else is just under 1% of the computational requirements. So it's just really the force that's hard to be computed here. And he used this Mark C GPU cluster for his simulations. This is the Maryland Advanced Research Computing Center, where they have all kinds of computers. There's 48 GPU nodes with, as far as I know, 2 NVIDIA K80 GPUs per node. And there's 48 of these. And this is the scaling of the algorithm. So the x-axis is the number of GPUs used to calculate the force. And this is the speed up here, and the theoretical limit is the solid black line. And he's pretty close to the theoretical limit. So this is an easily parallelizable problem, of course. But the whole thing is limited by the memory in the GPUs, so we cannot scale it up to the level of the state-of-the-art numerical cosmological simulations. But because it's a special simulation, it has its purposes when the goal is to compare these simulations with actual observations, where we have this spherical geometry and decreasing resolution as we go away. And many applications require computing the correlation functions in a wide range with a very high dynamic range, from the very shortest correlations to the longest distances, and these kind of simulations might help there a lot. And of course, GPUs help here a lot. So we are very thankful to AMD and NVIDIA. Okay, thank you very much.
Not really a question, just a comment. I think if you move on to the newest generation of GPUs, then you can use managed memory, and basically you have unlimited memory from the host. They have hardware support for host device, DMA, and memory paging. So that problem will be solved.
Hopefully, thanks.
Any other comments or questions? Okay, let's thank László.